Let's talk about electricity. And right away, I want you to think about something. You flip a switch, the light comes on, instantly, no delay. You're standing here, the switch is here, the power plant is 50 miles away, but the light comes on the moment you flip that switch. How? Most people say, well, electricity flows through the wires, like water through a pipe. And that seems reasonable. Electricity flows from the power plant through the wires into your house, through the switch into the light bulb. It's a flow, a current. Makes sense, except it's completely wrong. Electricity doesn't flow, not in the way you think, not in the way we teach it in school, not in the way that makes intuitive sense. And once you understand what's actually happening, once you see what electricity really is, you'll never look at a wire the same way again. Okay, let me show you the problem. Take a wire, copper wire, let's say, 1 meter long. You connect it to a battery. The battery pushes electrons through the wire. That's current. That's electricity flowing, right? Fine. Let's measure how fast the electrons actually move. They move slowly, incredibly slowly, about 1 millimeter per second, sometimes even slower. 1 millimeter per second, that's a snail's pace. That's nothing. At that speed, it would take an electron 16 minutes to travel 1 meter. But here's the thing. When you close a circuit, when you flip a switch, the effect happens almost instantly. Not 16 minutes later, right now, immediately. So if the electrons are moving at 1 millimeter per second, how does the light turn on instantly? That's the paradox. That's what we need to explain. Here's what people don't realize. The wire is already full of electrons. Before you even connect the battery, before you flip any switch, the copper wire is packed with free electrons. Trillions and trillions of them just sitting there, waiting. Copper has this property. Its atoms hold on to most of their electrons tightly, but the outermost electron from each atom is loose, free to wander. And in a typical wire, you've got about 10 to the 23rd free electrons per cubic centimeter. That's an enormous number. The wire is absolutely stuffed with electrons. Now, here's the key insight. When you close the switch, when you connect the battery, you don't send electrons from one end to the other. You push on the electrons that are already there. Think of it like a pipe full of water. If the pipe is already full and you push more water in at one end, water comes out the other end immediately. You're not waiting for the water you pushed to travel the length of the pipe. You're pushing on water that's already there, and the effect propagates instantly. Same thing with electrons in a wire. The wire is already full. You push on one end. The electrons at the other end respond immediately. Not because individual electrons moved fast, but because the push itself travels fast. How fast does the push travel? Nearly the speed of light. About 2/3 the speed of light for typical wires. So the electrons themselves are moving at 1 millimeter per second. But the electromagnetic push propagates at 200,000 kilometers per second. That's why the light comes on instantly. Not because electrons race through the wire, but because the electromagnetic push traveled at nearly light speed, and the electrons at the other end responded to that push. This changes everything about how you think about circuits. The electrons in your light bulb aren't the same electrons that left the power plant. They're just electrons that were already sitting there in the wire, and they started moving when the electromagnetic push reached them. Now here's where it gets really strange, and this is going to bother you. You've got power flowing from the power plant to your house. Energy is being transmitted. Your light bulb is getting hot, producing light. Energy is definitely going somewhere. But if the electrons are barely moving, how is energy being transported? The answer is going to sound wrong, but it's correct. The energy doesn't flow through the wire. The energy flows through the space around the wire. Let me say that again. When electricity powers your house, the energy is traveling through the air around the wires, not through the wires themselves. The wires are just there to guide the energy flow. They're like guardrails. The energy is flowing in the electromagnetic field that surrounds the wires. This is called the Poynting vector. It describes the direction and magnitude of energy flow in an electromagnetic field. And if you calculate it, if you actually work out where the energy is going, you find that it's flowing through the space around the wire, not through the interior of the wire. So if the energy isn't flowing through the wire, what are the electrons doing? Well, the electrons are moving slowly, about 1 millimeter per second. And as they move, they're carrying charge. That's the current. But they're not carrying the energy. The energy is in the field. Think of it this way. You've got a river. Water is flowing. That's like the current, the electrons moving. But you've also got waves on the surface of the river traveling much faster than the water itself. Those waves can carry energy downstream way faster than the water moves. The electromagnetic field is like those waves. The field carries energy at nearly light speed. The electrons just drift along slowly, maintaining the current that creates the field. This is deeply weird. It means that when you turn on a light, the energy that powers it doesn't actually travel through the copper in your walls. It travels through the insulation around the copper, through the air in your walls, through the empty space. The copper is just there to set up the right electromagnetic field configuration so that energy flows in the right direction. Let me give you a thought experiment to make this even more strange. Suppose you have two long parallel wires, very long, stretching for miles. At one end, you connect them to a battery. At the other end, miles away, you connect them to a light bulb. Now, when you close the circuit, how long does it take for the light bulb to turn on? If energy has to travel through the wires, it should take microseconds. The time for light to travel a few miles. But here's the thing. The energy doesn't have to go all the way down the wire and come back. The electromagnetic field can take a shortcut. Energy can flow directly through the space between the wires, from the battery to the light bulb, without going all the way down to the end. So the light turns on even faster than you'd expect, not because of anything traveling through the wire, but because energy flows through space along the shortest path allowed by the field. This was worked out in detail. It's not speculation. You can calculate exactly where the energy flows using Maxwell's equations, and it flows through space, not through conductors. You might be thinking, well, if the energy flows through space, why do we need wires at all? Good question. The wires do two things. First, they guide the electromagnetic field. The field wants to flow along the path of least resistance, and the wires provide that path. They shape the field, keep it confined, direct it where you want it to go. Second, the wires complete the circuit. You need a closed loop for current to flow. The electrons need somewhere to go. The battery pushes electrons into one wire and pulls them out of the other. Without that closed loop, you can't establish a steady current. And without a steady current, you don't get steady energy flow. So the wires are essential. But not because they carry energy, because they establish the electromagnetic field configuration that allows energy to flow through space. This is subtle, but it's important. The whole way we talk about electricity is misleading. We say current flows through the wire, when what we mean is charge drifts through the wire, creating an electromagnetic field that carries energy through space. But that's too complicated, so we simplify. And in simplifying, we hide the truth. Now what about resistance? Why do wires heat up when current flows through them? Well, the electrons are drifting through the wire, and they're colliding with atoms. Not literally colliding, because remember, atoms never actually touch. but they're interacting electromagnetically. The electrons are pushing against the electromagnetic fields of the atoms in the copper. Every time an electron interacts with an atom, it loses a little bit of energy. That energy goes into making the atom vibrate. And when atoms vibrate, we call that heat. So resistance is just electromagnetic friction. The electrons are trying to move, the atoms are in the way, energy is lost to vibrations, and the wire heats up. If the wire has low resistance like copper, the electrons can drift through relatively easily. Not much energy is lost. If the wire has high resistance, like a light bulb filament, the electrons have a hard time getting through. Lots of energy is lost. The wire gets hot enough to glow. That's why light bulbs work. You make the electrons squeeze through a very thin filament with high resistance. So much energy is lost that the filament heats up to 3,000 degrees and emits light. But again, the energy isn't flowing through the filament. It's flowing through the space around the filament. The filament is just where the energy gets converted from electromagnetic energy into heat and light. Now let's talk about AC, alternating current, because this is where things get even stranger. With direct current, DC, the electrons drift in one direction, slowly but steadily. The current flows from the battery through the circuit back to the battery. But with alternating current, the voltage flips back and forth, 60 times per second in the US, 50 times per second in Europe. That means the electrons aren't drifting in one direction. They're vibrating back and forth. How far do they move? Not far at all. Maybe a fraction of a millimeter. They just jiggle back and forth, 60 times per second. But power still flows. Energy still gets transmitted. Your house still works. How is that possible if the electrons are just vibrating in place? Because again, the energy isn't carried by the electrons. The energy is in the electromagnetic field. The field oscillates at 60 hertz, and that oscillating field carries energy through space at nearly light speed. The electrons are just there to maintain the oscillating current that creates the oscillating field. They don't have to go anywhere. They just have to move back and forth, and that's enough to set up a field that can transmit power. This is how the entire power grid works. Every outlet in your house, every appliance, every light, it's all running on electrons that are just vibrating back and forth, barely moving at all, while electromagnetic fields carry energy through space all around you. So let's come back to the fundamental question. What is electric current? We say current is the flow of charge. Okay, fine. Charge is flowing. Electrons are drifting or vibrating. That's current. But the thing you have to understand is that current isn't the energy. Current is just the motion of charged particles. Energy is in the field. You can have huge amounts of current with very little energy. You can have very little current with huge amounts of energy. They're related, but they're not the same thing. When you think about electricity, when you're trying to understand circuits, you have to keep track of two things: the current, which is charge moving through conductors, and the energy flow, which is happening in the electromagnetic field, in the space around the conductors. Most of the time, we ignore the field. We pretend that energy flows through the wires because it's easier to think about. And for practical purposes, it doesn't matter. The math works out the same either way. But if you want to really understand what's happening, if you want to know what electricity actually is, you have to think about fields. This is the part that people have trouble with. Fields seem abstract, mathematical, not physical, but fields are real. The electromagnetic field is a physical thing that exists in space. It has energy. It has momentum. It can exert forces. It's not just a calculational tool. It's actual stuff. When you turn on a lamp, you're creating an electromagnetic field that carries energy through space. That field is real. It's there. If you had the right equipment, You could detect it, measure it, map it out. And that field is doing the work, not the electrons. The electrons are just there to set up the field. The field is what matters. This is a complete inversion of the usual way we think about electricity. We think the electrons matter and the field is secondary. But actually, the field matters and the electrons are secondary. The electrons are just sources of field. They create field, they respond to field, but they're not the main event. The field is the main event. Now you might be thinking, okay, fine. Energy flows through space, not through wires. Why does that matter? Why should I care? Well, first, because it's true, and truth matters. If you're going to understand the world, you should understand it correctly, not through comfortable oversimplifications. But second, because this insight explains things that the simple electricity flows like water model can't explain. For example, why does a capacitor work? A capacitor is just two metal plates separated by an insulator. No current flows through the insulator. The circuit is broken. And yet, a C current can flow through a capacitor. How? Because the current isn't what matters. What matters is the electromagnetic field. The field can exist between the plates even though no electrons cross the gap. And that field can carry energy. So power flows through the capacitor even though current doesn't. Or consider an antenna. You've got electrons oscillating up and down in a piece of metal, and somehow that creates electromagnetic waves that travel across miles of empty space. How? Because moving charges create changing electromagnetic fields, and changing electromagnetic fields propagate through space at the speed of light. The electrons are just sources. The field is what travels. Or think about transformers. You've got two coils of wire not even touching each other. You run a C through one coil and current appears in the other coil. How? Magnetic fields. The changing current in the first coil creates a changing magnetic field. That changing magnetic field passes through the second coil. The changing magnetic field pushes on the electrons in the second coil. Current flows. No physical connection, just fields interacting through empty space. And this gets to the deepest thing about electricity. Electricity and magnetism aren't two separate phenomena. They're different aspects of one unified electromagnetic field. Moving charges create magnetic fields. Changing magnetic fields create electric fields. They're inseparable. You can't have one without the other. When you flip a switch, you're manipulating the electromagnetic field. That field has both electric and magnetic components, and they're linked together, feeding off each other, creating patterns that propagate through space at light speed. That's what electricity really is. It's not a substance flowing through wires. It's a disturbance in the electromagnetic field that permeates all of space. The wires just give the disturbance something to push against, a way to transfer energy from one place to another. But the energy itself, the power, that's traveling through space, carried by fields. So let's come back to where we started. You flip a switch, the light comes on instantly. Here's what actually happens. You close the circuit. The battery starts pushing on electrons throughout the entire circuit. Those electrons start drifting slowly, about 1 millimeter per second. But the electromagnetic push travels at nearly light speed. The push reaches the light bulb almost instantly. Electrons in the filament start moving. The filament resists. Energy flows through the space around the filament, gets absorbed by the filament, converts to heat. The filament glows. Electromagnetic waves radiate outward through space. Some of those waves hit your eyes. Your retina responds. You see light. None of this is happening inside the wires. It's all happening in the space around the wires, in the fields, in the electromagnetic disturbances propagating through what seems like empty space. But that space isn't empty. It's full of fields, always has been, always will be. And when you understand that, when you really understand that the world is made of fields, that forces propagate through space, that energy can flow without anything physical carrying it, everything changes. You realize that wires are just guides, that electricity isn't the flow, that the energy powering your life is traveling invisibly through the air all around you. That's what electricity actually is, not a current in a wire, a disturbance in the fundamental field of reality. And we learn to manipulate that. We learn to create those disturbances, control them, use them to do useful work, to light our homes, power our machines, transmit information across continents, all by manipulating fields, by pushing on electrons just enough to create the right patterns in the electromagnetic field. That's the real story, not the story we tell in school, not the comfortable lie about current flowing like water. The truth, the strange, counterintuitive, absolutely beautiful truth. Electricity doesn't flow, fields do, and that changes everything.